Hello and welcome to this video on calculating triple integrals. Alright, so let's consider the following. So this right here is a triple integral. So I have the integral from 0 to 2, the integral from 0 to 3, the integral from 0 to 4 of x, y squared, z cubed, dx, dy, dz. This is called a triple integral, and it's evaluated the same way an iterated integral is calculated, with the addition of a third step of integration. And again, if you remember, we work inside out. So this dx here, the endpoints for x are from 0 to 4. This dy, this is the endpoints on y from 0 to 3. And this dz, this is endpoints on z from 0 to 2. Now, if you remember with your iterated integrals, the integration represented an area on the xy plane. Well, this now represents a volume, a shape in the xyz space. So if you were to plot this, this is actually going to be a rectangle. So, not a rectangle, this is a rectangular solid. So along the x, it goes from 0 to 4. Then along the y, it goes from 0 to 3, and then along the z, it goes from 0 to 2. So this creates a rectangular solid that we're integrating across, and here's a function that's defined in that rectangular solid. And if this right here was like maybe a density function for values of x, y, and z inside of our rectangular solid, then what this triple integral calculates is the mass of that rectangular solid. So just like in 2 dimensions, this is now a 3-dimensional equivalent of that iterated integral. So let's go ahead and integrate this. The process is pretty much the same. So the solution to this, if I integrate with respect to x, add 1 to the exponent, divide by the new exponent, and then I have to plug in my endpoints, bringing my 1/2 out. That gives me 4 squared times y squared z cubed minus, when I plug in 0, that's going to be 0 squared, which is 0, times y squared times z cubed dy dz. And this calculates to a 16 y squared z cubed, and then pulling the 16 out, 1/2 times 16 gives me an 8. Now I'm going to integrate with respect to y. So integrating with respect to y, add 1 to my exponent, divide by my new exponent. So that gives me 1/3 y to the 3rd power, going from 0 to 3. Pulling my 1/3 out, that makes this 8/3, and then plugging in my endpoints. So that gives me 3 cubed times z cubed minus 0 cubed times z cubed, which will end up giving me 27 z to the 3rd power dz, with an 8/3 out in front. So if I pull my 27 out, the 27 and the 3 reduce, that leaves me with a 9, and 9 times 8 is 72. So I now have 72 times the integral from 0 to 2 of z to the 3rd power dz. So integrating with respect to z, so I add 1 to the exponent, which gives me a 72 over 4, and then z to the 4th power. So add 1 to the exponent, divide by the new exponent, and I'm evaluating this from 0 to 2. 72 divided by 4, that gives me an 18. So I have 18 times 2 to the 4th power minus 18 times 0 to the 4th power, which calculates to 288. So calculating your triple integrals is going to be the same thing as calculating the double integrals. It's just going to have one more additional step. And remember that when you take a look at your endpoints for your triple integrals, that describes a 3-dimensional volume rather than just a space on the xy plane. So this lesson is almost the same as the iterated integral. In 2 dimensions, we just added a 3rd dimension into it. Thank you for watching, and I will see you next time.